Okay, so good morning. I wanted to talk real quick about how graphs can help us understand an ecosystem and help us understand interactions between populations. And generally in ecology, we see two types of graphs. And you can ignore the questions and stuff like that. I'm mostly just using this document because they have some really good graphs on them. So the two types of graphs we normally see is exponential and logistical growth, or death. Exponential growth is this one here. And so what exponential means is every kind of, in this case, year or generation, you get a large amount of growth, all right? And it makes this U curve. All right? So if you've taken math, when you get formulas that have exponents like x squared, you start getting this shape of graph. And that's what they mean by exponential growth, is because if you were to express it mathematically, your formula would have exponents in it. And that's what gives you kind of this gradual sharp upturn. And then logistical growth is kind of this more gentle curve to it. So it can't be expressed with exponents, but there's some growth. That's why it's going up. Another thing we can see in a graph is carrying capacity. So carrying capacity is how much can an ecosystem support. So in this case, this is white-tailed deer from 1985 to 1995, so for a decade. And so this is the population. This is the timeline, so that's why we're using the line graph, because it's over time. And then you can see that they weren't doing too good in 1985, and maybe some deer were introduced to this area at that time. And then over time, they experienced what looks like exponential growth, right? Because it has that U curve, and it kept going. But eventually, at some point in time, the ecosystem doesn't have any more food. It doesn't have any more water, and things like that. And the white-tailed deer can't survive anymore. And so you kind of get a die-off, and they drop below what the carrying capacity is. And then let's say there was a good year of rain, or a good 5 years of rain, so there was a lot of plant growth. And so the carrying capacity was temporarily increased. Right, so we can get this big loop up here, but it doesn't last forever, and eventually there's some more deaths than births, and so the population goes down. Carrying capacity, like I said, is how much can the ecosystem support as far as population goes. And so ecologists can use this to kind of see the health of the ecosystem and know like what's a healthy population of white-tailed deer or some other type of animal. But so graphs like this tell us, the carrying capacity for the ecosystem, exactly what it says. I'm going to skip survival graphs right now. Okay, competitive exclusion. I included this in one of the slideshows, presentations that I did. If you had these are two species of bacteria. If you had either of them grow by themselves, this dotted line is the expected growth over, looks like about 30 days. Okay. But if you grow them together, okay, because they compete for the same resources, so whatever nutrients are in the petri dish that they're growing them in, okay, you can see that this one here, which is sorry, it starts with a C, caudatum, it grew really fast, and it's probably using a lot of resources, but then it was competing with itself, so it kind of hit maybe the carrying capacity of that petri dish and started dropping a little. This was more gradual, and so it was able to adapt to its environment and survive. But because this one was doing so well, this one started doing so bad. Right? It's that competition. Right? So competitive exclusion principle tells us that no two organisms can occupy the same niche at the same time in the same place, right? Because they would outcompete each other, and eventually one would die off. Okay, and that we can see that in bacteria right here. All right, so again, a graph teaches about competitive exclusion. Okay. Here we see a predator and prey graph. Right, so the kind of pink purple is a moose, the blue are wolves, And so we can see here, there's a slight increase in the moose population, and we see a huge increase in the wolf population. Right? So there's a pattern here. You see an increase in moose, then you see an increase in wolves. Okay? And then you see a sharp decline in wolves right here. That's because they went way over their carrying capacity. Okay? And part of that is this dip here and moose, right? So this high here is related to the high there. That's why you got it. But because it started declining, there wasn't enough food to support the wolves, and they dropped hard. So there might have been something else going on. But because they dropped here and there was less predation, okay, we see this increase in moose right here. Okay, so there's a connection, right? As there's more moose, there's more wolves because there's more food for them to eat. As there's less wolves, there's less hunting, and so it leads to more moose. Okay, and so it's kind of a gentle connection. And as you can see here, the lines start getting closer and closer because they're reaching an equilibrium here. And I just want to read this real quick. Remote island established 1940, doesn't can only get there by boat or seaplane. Moose first arrived in the Isle Royale around 1900. The moose population tends to increase in years with mild winters. Early spring green up, abundant winter foliage. So, you know, how the environment is doing will give us a different moose population. Low wolf numbers and low levels of tick infestation. Wolves first arrived at the island on an ice bridge from Canada in 1940. So the moose had like a good 40 years to grow, develop, and kind of fit the carrying capacity of the island before wolves showed up. Disease has also influenced the wolf population between 1980 and 1982. So just looking at the graph, I knew there was something more than just the moose population connected to that. And then when I finally come up here and read, there was parvo. And so they had a huge decline. And because of that huge decline, we get that uptick in moose population. Because of that uptick in moose population, you start getting an uptick in wolf population. Right, so you had that huge decline. You had a slight rebound, but it looks like parvo was probably still going on, and it took some time to recover. And here we're seeing them getting more into an equilibrium with each other, right, hitting that carrying capacity. Right. So predator-prey graphs will give us a pattern or a connection between what's being eaten and what is what's doing the eating. So the predators and the prey. And then, like I said, this right here, if I was an ecologist and I saw this graph, I'd say, wow, what happened in 1980? I'm going to do more research, right? And that can help us learn new things. Okay, so that's kind of the basics of graphs that you see. Kind of the ones I want you to concentrate on is this predator and prey one, and look at the patterns connected between predator and prey, food and what's doing the eating. Okay? And kind of these population ones, because we can see competitive exclusion, and then we can also see carrying capacity and these things right here. So more carrying capacity ones that you might see is they'll come up and they'll actually peak a little, and then they'll kind of just start leveling off, and then it'll hover just under the carrying capacity. All right, I hope this was helpful. Have a good day.